Hello there. My name is Gavin Fisher and I'm an applications engineer from FormFactor. I'm with the Centre of Expertise. I'm stood here now in Milan in European Microwave 2022 and in front of you you can see a system that we have which is currently operating in our laboratory in Dresden, or it's actually Saka near Dresden. It's an awful lot easier to take a screen than it is to take an entire prober. Although we do have an entire prober just over here, which is doing single sweep work up to 170 gigahertz. But for today, I want to show you the fact that we have a prober that we're operating remotely from a trade show, and it's working very nicely indeed. So the system that you can see here, over this corner, this is a Summit 12,000 probe station. It's a 200mm prober that we have produced for a number of years, and this has been augmented using our autonomous RF measurement assistant. The solution comprises our microscope, which most of our customers would have on these kind of machines, and a pair of motorized RF positioners. On these motorized positioners, we have mounted some arms using the Keysight N5291A system. This can go up to 130 gigahertz, though we've currently got it set up to 110, and we're using a pair of Infinity probes, Infinity 110s, although you can't see them as they're nestling inside this chamber. The reason why we have that chamber on there is so that we can do over temperature measurements in a dark, dry and shielded environment to do the most demanding on-wafer characterization work. So you might say, well, what's so special about all of that? That's kind of standard stuff and it's been around for a while, and that would possibly be true. But one of the really nice things is that I have been, particularly during the period of lockdown, operating this machine, this very machine in fact, remotely from my house in the United Kingdom. It kept me sane during lockdown and enabled me to continue working. And this is the same machine that you can see operating today. And what we're doing is we're allowing this machine to work continuously on its own. It's autonomous. It's got a Python script to operate it, and what we're doing is we're making a series of measurements of a wafer of our own. It looks very much like impedance standard substrate, but it isn't. It's a series of test structures, and the machine is operating continually on its own. When it's doing this work, it's able to calibrate entirely on its own, and if the calibration is successful, it will then continue, move to the wafer, and then move to the various sites it needs to measure, including adjusting the geometry from one site to another. So we literally do not have to touch the machine at all. And what's more, it's able to do this work over temperature. So we can take it, transition from one temperature to another, and the machine is able to adjust the probe geometry to maintain a constant spacing between the probes without any risk of damage. So it is a real boon for a lab, because it means that the single person who would normally be almost nursemaiding machine for a thermal transition and thermal work is then freed up to do a lot of other things. So that's really very good. Let me just minimize the screen for a moment. So right now you can see it's making a series of measurements. This thing we're flashing here is this is our WinCal calibration software. And let me just stop this for a moment. Stop our script. So it's testing complete, so it's actually finished its run. And let me just show you a few things. So if I, for instance, right now decide, I want to get a calibration on my machine, but I don't want to have to adjust the geometry. Look, the geometry is spaced out here. I don't want to adjust that. So what I can do is just press this button, and the system's now going to go and run through a calibration sequence. Just try and get this out of the way. So the first part of the calibration sequence is we want to clean the probes. We want to clean the probes to make sure we haven't built up any contaminant or have anything which would otherwise affect the calibration we're trying to do. Now this happens over temperature, so we've got to be able to know that we can accurately find that cleaning media without any damage to our probes. We do this by looking for a fiducial. Effectively this time we're using a corner of the auxiliary chuck fence, and it knows the offset from that point to the cleaning media. So we come and it's going to go to hit the cleaning media very quickly. And in this case we make 9 cleaning cycles. Now we're going to go to the impedance standard substrate, And now we're going to find a fiducial on here. So we're looking for this S shape that you can see, and the system's able to know where that is, and then it's going to find the probes. You can see I'm highlighting the probe tips. And if necessary, it's going to make a series of adjustments in X, Y, and Z, so each probe is within the tolerances that we expect. So you might see a few little bit of iterations. It's looking for a final distance of 130, an initial of 150. 170, because there'll be a 20 micron scrub per probe. You also see we've got augmented align, so these marks would be useful if I was a user doing some manual work, but I don't need to worry about that. The system is purely doing that all on its own. So with that done, the system's going to run its auto calibration. If it were doing anything over temperature, it would be in fact doing a stabilize as well at this point, so it'll be stabilizing the probes, getting them back up to operating temperature at the wafer. And then with the calibration done, we would stabilize again, assuming the calibration is successful, so hopefully it will be. If it isn't, it won't let me out. It will go and do it again. We're just on the load right now. All real. And so now we're going to go, and if we're at temperature will be stabilizing, again warming the probes back up. And then once this is complete, we'll run a validation and a monitor. So basically we're going to go grab the monitoring data from it. The monitoring data will use us to make sure that we know that the calibration is still good at a later time. Why do we do this? Well, the systems do basically drift as a function of time, and we want to know that any measurement that we make is a valid measurement. So what you're looking at here is a Python script, and the intention of this Python script is we're going to do a transition up to a temperature of 55 degrees C, so it's done the transition already, and the system is soaking. And once we're at the operating temperature, the system should initiate a calibration sequence, which we may speed through in this video, and then we'll actually run through and show it moving from structure to structure and doing its monitors, or we may do its monitors. It's optional for the system, depending on how many die steps it's done. Let me just get this out the frame. So you can see the system gives you full status of how it's doing. You can see the soaking time. It tells you how much it's got to soak. In this case, we have a somewhat artificial time of only like a couple of minutes. But once it's finished its soaking, it will then go and do its various alignments, recalibration, and then we'll go to measure the structures on the wafer. And incidentally, it can do this even with a very simple Python script. It can basically take those measurements directly from WinCal, but more often than not, this would be done by a customer test executive, such as Wafer Pro or Wafer Pro Express from Keysight. So now it's just entering the calibration sequence which we saw earlier. So we'll probably cut through this in our video. And at the end of the calibration, we'll move back to the wafer with the intention of stabilizing the probes, getting them warm and back up to temperature. And then we perform a validation work that checks basically the calibration against a model. And it will then also do a monitor measurement, and the monitor measurement grabs a trace and uses that to do a comparison against at any given time to make sure your calibration hasn't drifted. That's really important for our customers because they want to make sure that any measurement they do is basically within the specifications expected. Now, that monitor activity is done purely at customer's behest, so it can select the number of cycles, number of die moves, subsite moves, and all those kinds of things are settable all the time. System now is doing an alignment of that wafer. It's a view track align, make sure it's all correctly aligned, which is useful at temperature. Not essential because the system does do adjustment from each die step. And with that done, it will basically be viewing its transition as being complete, and then it effectively hands over the prober back to the test executive. All the activities that you just saw happening a moment ago were purely autonomous. The test executive did none of those things. It was purely the system getting itself in a state, corrected and ready for work, ready for measurements. But after it hands it back and it's done its dye soak, make sure it's stabilized, and then it will start going to its test sites. So the scans that you can see is the system looking for the probe tip, finding in focus to know what height it's gone to, and then finding pattern recognition XY offsets. If it's different from the expected or trained dimension, it will make adjustments in X and Y using the motorized positioners. So it should now step to its first actual official test die. It's got a little delay in my script. So we now get to our first official test site. And you can see we made contact. Now you can see it's going to be taking a measurement of that location in a WinCal report. And now it should move to a different geometry device. And it's purely using the Velux wafer map for this. So there's nothing special. My script doesn't have to know these positions. It's purely contained in the Velux wafer map. So if you want to test them yourself, you literally just move there, just click that location, and you'll get the same effect. And then it will progress for the whole wafer. It will do a dye step. If required, it will do a monitor to check that its data is going to be valid. If the monitor's failed, it recalibrate. If it hasn't failed and it's valid, it just goes and continues to measurement. And that enables you to do simple, accurate measurements, unattended and remote.